Yes, I'm V. John Reddy, Assistant Professor in the Department of Physics from Nalla Narasimha Reddy Engineering College. Today we are going to discuss about a small topic regarding lasers. Okay, first of all, what is the laser? Laser is an artificial light source. It emits the light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. So laser is an artificial light source. It emits the light on the process of optical amplification based on the stimulated emission of electromagnetic radiation. Laser is an artificial light source, and ordinary bulbs, flash lamps, these all are also artificial light sources. But there is a huge difference between these two, lasers and ordinary light sources. The laser light is having the few specific characteristics compared with other ordinary light sources or LEDs. Those are, it is having the highly monochromatic, and it is having high directionality, and it's having highly coherence. The laser light is having highly coherence, and it is having high directionality. Okay. Those are the special characteristics of laser light. There are four characteristics. Those are high directionality, high intensity, high coherence, and high monochromicity. And we can call the term laser is acronym for light amplification by stimulated emission of radiation. Laser stands for light amplification by stimulated emission of radiation. And this stimulated emission was explained by Albert Einstein in the year of 1917, and based on his hypothesis, Myman is developed first laser, that is ruby laser, in the year of 1960, and there is a few basic concepts in the lasers. Those are, we can call the mechanism of light emission. The first one is stimulated absorption, or simply we can call absorption. Absorption. What does it mean by absorption? First of all, if you take an atom, and the atom contains n number of particles or electrons. These all the electrons are located at the lower energy levels. Here we are taking the two energy levels, one E1 and E2, where E1 is the lower energy state and E2 is the higher energy state. If a photon, here we are instant few photons on the lower energy state, those photons is absorbed by the electron and they are excited to higher energy state. Here the photon energy is the energy difference between the E2 and E1. Okay, in the absorption, if a photon of energy h nu, E2 minus E1, that energy is E2 minus E1, is collides with an atom present in the ground state of energy E1, then the atom completely absorbs the energy incident photon and makes transition to excited state, that is E2. This process is we are called the absorption. In the absorption process, the ground state atoms absorb the energy and they are excited to higher energy state. Photon is incident on ground state E1 atom, and that is absorbed and that is enter into higher energy state. Next, this excited state atoms is unstable. This excited state is unstable for the atoms. Okay, the atoms is present in the excited state very small lifetime, that is in 10 to the power of minus 8 seconds. After the time, the atoms comes to ground state. One is voluntarily and another one is forcefully. If the atom comes to ground state voluntarily after its lifetime, that is we are called the spontaneous emission. If the atom comes to ground state before its lifetime, that is we are called the stimulated emission. The first one is spontaneous emission. An atom initially present in the excited state makes transition voluntarily on its own without any aid of external stimulus or an agency to the ground state and emits a photon of energy h nu equals to E2 minus E1. The period of stay of the atom or electron in the excited state is called the lifetime. The process of emission of light is called the spontaneous emission. The spontaneous emission, actually the atom is presented in the higher energy state, and from the higher energy state, after its lifetime, the atom comes to ground state by emitting the one photon. That photon energy is the energy difference between the two energy states, that is h nu equals to E2 minus E1. This is spontaneous emission. In the spontaneous emission, the atom comes to ground state after its lifetime. This phenomena is explained by Niels Bohr. The next one is stimulated emission. In the stimulated emission also, the atom is present in the higher energy state, but here we incident and photon, which energy of photon energy is the energy difference between two energy levels, that is E2 minus E1. Before its lifetime, we incident the photon on the excited atom before its lifetime. Due to this excited atom, the atom is get excited and comes to ground state forcefully, and by emitting the two photons. The incident photon is not utilized, that photon is emitted and extra one photon is emitted. Here we are getting the two photons. Okay. The stimulated emission, a photon having energy h nu E2 minus E1 incident on atom present in the excited state, and the atom is stimulated to make transition to the ground state. This gives off a photon of energy h nu. The emitted photon is in the phase with the incident photon. These are coherent. This type of emission is known as stimulated emission. This is here we are observing the before stimulated emission, the atom is in excited state. Here we are incident one photon on the excited state. Due to this photon, the atom comes to ground state. After stimulation, it emits the two photons. One photon is incident photon and another photon is emitted photon. Here we are getting the two photons, and these two photons are coherent. Okay, this is stimulated emission. This stimulated emission was explained by Albert Einstein in the year of 1917. Theoretically, he explained, but he did not done any experiment on this stimulated emission. Based on the His hypothesis, in the 1960, first laser was developed. The next one is the few differences between the spontaneous and stimulated emission of radiation. First of all, for spontaneous emission. Spontaneous emission is a polychromatic light. Polychromatic light, or we can call polychromatic radiation. Polychromatic means it contains the n number of wavelengths, many number of wavelengths. It's a monochromatic radiation. Stimulated emission is monochromatic radiation. The next one, spontaneous, has less intensity. The stimulated emission is having the high intensity. Spontaneous emission is having less directionality and more angular spread during the propagation. It has high directionality and so less angular spreading during the propagation. Spontaneous is incoherent and stimulated is coherent. The spontaneous emission light is not amplified. Stimulated emission light is amplified. Spontaneous emission takes place when the excited atoms make a transition to lower energy level voluntarily without any external stimulation. The stimulated emission takes place when a photon of energy equal to h nu, that is E2 minus E1, stimulates an excited atom to make transition to lower level. In a single downward transition, spontaneous emission results in the emission of one photon. In a single downward transition, the stimulated emission results in the emission of two photons. The example of an ordinary electric bulb and LED, light from an LED, there is a light from light source. The spontaneous emission was explained by Niels Bohr, and stimulated emission was explained by Albert Einstein. The next one is characteristics of laser light. The most important characteristics of laser beam are highly monochromatic, high degree of coherence, high directionality, and high brightness. So first of all, first one is monochromicity. What is meant by monochromicity? Monochromicity means simply in a single wavelength. The laser light is monochromatic or very pure in color. The laser beam is in single wavelength, that is, a line width of the laser beam is extremely narrow. The line width of the laser beam is extremely narrow. In conventional light sources, the wavelength spreading is usually 1 in 10 to the power of 6. In case of laser light, the spreading will be 1 in 10 to the power of 15. This means that if the frequency of radiation is 10 to the power of 15 hertz, then the width of the line will be 1 hertz. The spreading is 10 to the power of 15. The frequency of the radiation is 10 to the power of 15 hertz, then the width of the line will be very less, that is 1 hertz. The next one is directionality. Laser beam emits light only in one direction. It travels very long distances without divergence, and so laser communication is carried on between the earth and the moon. The directionality of a laser beam is expressed in terms of divergence. Suppose R1 and R2 are the radii of a laser beam at a distance d1 and d2 from a laser, then the divergence d theta or delta theta equals to R1 minus R2 by d2 minus d1. Here we are saying that the laser light is traveling a large distances. Here suppose I am taking the one point d1 A and another point is B. The distance between the source is d1 and d2. From source to point A d1 and from source to point B d2, and the spreading of the light is at A is R1, at B is R2, and the divergence we are taking d theta equals to, or delta theta equals to R1 minus R2 by d2 minus d1. The spreading is very less. The divergence of a laser beam is 0.01 milliradian, where in case of such light is its 0.5 radiation. Other light is having the high divergence, but laser light is having very less divergence. That's why it is having the high directionality. And another reason is, for the high directionality, when the laser light is emitted from the source, it is emitted along the parallel to its axis. The emission of the laser light is parallel to its axis. That's why it is having the high directionality. This is also one of the reasons for the high directionality. The next one is coherence. What is meant by coherence? We can say the coherence means if the two sources of light are said to be coherent if they have zero or a constant phase difference between them, then that is we are called the coherent sources or coherence. Laser beam is both spatially and temporally coherent. If you observe here, sunlight is incoherent. The sunlight is having the many wavelengths on it. Those all are different, travels in the different directions and the different colors. This is incoherent, the first one. The second one is LED. LED is, and even the LED is monochromatic, but it is not contains the coherence. In these waves, there is no constant phase difference, or there is no zero phase difference. But you can observe the laser beam. The laser beam is having the coherent. The laser beam is having the coherent. The coherence is also the spatially and temporally, both are coherent. The temporal coherence. Temporal coherence refers to the correlation between the light fields at a different times at a point on the wave. Okay, the temporal coherence refers to the correlation between the light field at a different times at a point on the wave, different times at a point on the wave. You can observe the continuous waves P1 and P2 points. At any time, that is, you observe at different times, that is showing the same. If it is a discontinuous wave, that is in the P1 and P2, those two are not carrying coherence. Temporal coherence refers to the fact that the wave is polarized and retains the same frequency and phase over the entire length of the beam. Hence, the laser have long coherence length. If there is no change in the phase order at time t at a point on the wave, then it is said to be temporally coherent during the time. Since two points P1 and P2 are on the same wave train, which is continuous, they have correlation. The next one is spatial coherence. If a wave maintains a constant phase difference or is in a phase at two different points on the wave over a time t, then the wave is said to be spatially coherent. The spatial coherence refers to the laser beam output being narrow and resistant and diffraction, essentially retaining its narrow shape. This allows the laser to be focused in a small spots as well as reach large distances. Small focus on a small spots as well as the reach. The next one is brightness. The laser beam is highly bright as compared to the conventional light because more light is concentrated in a small region. Here we know that in the spontaneous emission we are getting only one photon. In the stimulated emission we are getting two photons, and these two photons are constant due to the high directionality that is focused on a small point. That's why its intensity is more compared to others. It is observed that the intensity of 1 millivolt laser light is 10,000 times brighter than the light from the sun and the sun at the Earth's surface. Okay? The intensity is proportional to the square of the amplitude, and hence the intensity of the resultant laser beam is very high. Okay, the laser light is having the high intensity. The next one is, the concept is Einstein's coefficient. Here the Einstein is given the relation between the absorption, spontaneous emission and stimulated emission. Okay, here I am taking the E1 and E2 are the energy states, and N1 and N2 be the number of atoms per unit volume in the energy states, E1 and E2. Here let us start. Let N1 be the number of atoms per unit volume with energy E1, and N2 be the number of atoms per unit volume with energy E2. Let small n be the number of photons per unit volume at a frequency nu, such that h nu equals to E2 minus E1. Then the energy density of interacting photon rho v is given by rho v equals to nh nu. N is the number of photons per unit volume. H nu is the each photon energy. When these photons interact with the atoms, both upward, that is absorption, and downward emission transitions occur. At equilibrium, these transitions rate must be equal. The number of upward transition at equilibrium position means number of upward transitions equals to number of downward transitions. Here is upward transition is absorption and downward transition is spontaneous emission as well as stimulated emission. The first one is upward transition, or we can call it stimulated absorption. Stimulated absorption rate depends on, here the stimulated absorption depends on two factors. One is the number of atoms present in the ground state, and second one is number of photons incident on the ground state. On these two factors, the absorption is depends. The stimulated absorption rate depends on the number of atoms available in the lower energy state for absorption of these photons as well as the energy density of interacting radiation. That is, stimulated absorption rate is proportional to N1 and is proportional to rho v, that equals to B122 N1 rho v, where B122 is the Einstein's coefficient of stimulated absorption. Why here we are taking B122? The atoms is goes from 1 to 2. That's why we are taking B1 to 2. The next, coming to downward transitions. The first one is spontaneous emission. The spontaneous emission rate depends on the number of atoms present in the excited state. That does not depend on the energy. That's why the spontaneous rate is proportional to N2. This equals to A21 N2. A21 N2, where the constant is proportionality. A21 is the Einstein's coefficient of spontaneous emission. Here we are taking the 2 to 1 because of the atoms is comes from energy level 2 to 1. That is the A2 to 1. That is equation number 3. Next, coming to stimulated emission. Stimulated emission rate depends on two factors here once again. That is the number of atoms present in the higher energy state and external energy, photon intensity. The stimulated emission rate depends on the number of atoms available in the excited state as well as the energy density of interacting photons. That is, stimulated emission rate is proportional to N2 and stimulated emission rate is proportional to rho v, that equals to B221 N2 rho v, where the constant proportionality B221 is Einstein's coefficient of stimulated emission. Here B221, the atoms is coming from second higher energy state to lower energy state. Okay. For a system is in equilibrium, the number of upward transitions equals to number of downward transitions. That is, absorption equals to stimulated emission, spontaneous emission plus stimulated emission. Absorption N1 rho v B12 equals to N2 rho v B21 plus N2 A2. Take the common rho v and rho v equals to A2 N2 A21 by N1 B12 N2 B21 and rho v equals to A21 by B21 B12 by B21 N1 by N2 minus 1. If the population of the various energy levels in the thermal equilibrium is given by Boltzmann distribution law, as Boltzmann distribution law, Ni equals to Gi N naught e to the power of Ei by Kt. Now N1 by N2 equals to G1 by G2 e to the power of h nu by Kt, because N1 equals to G1 N naught e to the power of minus E1 by Kt and N2 equals to G2 N naught e to the power of E2 by Kt. N1 by N2 G1 by G2 e to the power of E2 minus E1 by Kt. E2 minus E1 value is, we know that there is a h nu. Okay, rho v equals to, then rho v equals, substitute N1 by N2 value in the equation 7, then we can get rho v equals to A21 by B21 by B12 by G1 equals to B21 G2 into e to the power of h nu by Kt. This is energy density. From the Planck's black body radiation, the radiation density is from rho v equals to 8 pi h nu cube by c cube into e to the power of 1 by e to the power of h nu by Kt minus 1. These two, equation 8 and 9, both are giving the energy density only. Compare these two equations, then we can get B12 equals to G1 B12 equals to G2 B21, means B12 equals to B21, absorption equals to stimulated emission only, and A21 by B21 equals to 8 by h nu cube by c cube. From the equations 10 and 11 are referred to the Einstein relations. These two are Einstein